Hello everyone, I'm Chris McIntosh. I help teach statistics courses. This week we're going over your week 14 computer assignment. We're going to conduct a multiple regression in Jamovi, interpret results, report results, and interpret a Bayes factor for a multiple regression. First, we're going to open the data set. You should have that on in your assignment page on Canvas, and it's the IQ data set. So you want to download that and open it. And I have it open right here. And add your name to the results. Just click on Exploration Descriptives and get a result page started, and add your name at the beginning there. This is pulling from the statistical analysis checklist for week 14 multiple regression. You should have the link to that and have updated your version of that. So questions in section 1, the study information. Again, this is a learning exercise. The data are fabricated and results are not generalizable. But if you were doing this for your own work, you'd want to describe what is the purpose of this study that you're doing or this project, and how generalizable are these results to other settings or situations. Some different research questions which may be answered by a multiple regression. Does blood lead level and mother's IQ predict child IQ? What is the best predictor for child IQ? What is the prediction equation for child IQ? There are a number of different types of questions that you can answer using a regression. The study design, this is similar to last week's data where it's looking at blood lead levels, and that would be unethical to randomly assign people to groups to have high blood lead levels. So this would most likely be some sort of a descriptive design where these things happened and people are studying it. No ethical considerations were described, and no information about data collection and handling, but in your own project you would want to describe those things so that you had that available for your research report. Questions in section 2, the data set information. What are the variables and level of measurement for each one? So if we looked at our data set and we have blood lead levels, and that is a continuous variable, and that would be more specifically a ratio level of measurement. Mother's IQ, also continuous. IQ is a psychometric type of instrument. If we were being more specific, although Jamovi doesn't make us be more specific than it's continuous, that would be an interval level of measurement. There's no such thing as a 0 IQ. And child IQ, again, another interval level of measurement. Data accuracy issues. So we'd want to get descriptive statistics for these. So we would go to, we can click on our descriptive since we already brought a block up. And we can just drag each of our variables over to the variables box. Since these are all continuous variables, we want means and standard deviations, which we have. A normality test on each one would be good, and seeing some plots. For continuous variables, we want histograms and box plots. So we can see we have 10 entries for each variable, nothing is missing. We have some means and standard deviations there, our Shapiro-Wilk tests. So we have a significant non-normality there for child IQ, so that might be something to look at. So at our plots for blood lead levels, we do have an outlier there for the blood lead level. It says it's number 10, so most people are down here. around 25, but we've got somebody that's pretty high up there at 100. Mother's IQ, no outliers there. And child IQ, we have this really high value up here. So let's go look at the data. And if we, tells us it's number 10, we can see on row 10, we have a child IQ of 811. So I've never heard of an IQ that high. That's a bit of a nonsense answer. So think to yourself, if I have an outlier this big, it's kind of a nonsense answer. What would I do about this? And these are data from the Heavy text. So if you went to page 194 and looked at the data, you would notice that child IQ, where we have a blood level of 100, mother's IQ of 95, the child's IQ is actually supposed to be 81. So I apparently fat-fingered this. I actually did it on purpose to give you guys a chance to see this, but these types of errors happen all the time, and you would want to investigate your really nonsensical answers, from your domain knowledge. I know that there's no such thing as an 800 IQ, and what you want to do is go fix it. So we have the original data set, and we can very easily go correct the mistake. So once we put that in, we see we have no outliers here in our output. So when possible, investigate and fix the error. It might be your data set, go fix a problem. You do not want to go analyze a bunch of data and then realize that you had this really bad outlier that you had not found, and all of your results are not going to mean anything. You also wouldn't just automatically exclude it from the data set if you could go fix it. If you couldn't fix it, that would be another story. That would be a good justification to exclude that participant from the data set when you had this big outlier and had no way to go check it and find out what was going on with it. So when possible, go fix it. Otherwise, leave it out. So we did have a couple of outliers and a couple of variables. One of them we fixed. One of them is just part of the data set. Data manipulation, we're not doing any other manipulation with the data. Missing data, there weren't any data outliers. We did see outliers. And we got our descriptive statistics. For regression, we do want to look at a correlation matrix and see how our variables, our predictors are correlated with each other, and how are they related to the outcome variables. So we're going to go to analysis, regression, and correlation matrix. So let's go take a peek at that. And we're going to move all of our variables over. Child IQ is going to end up being our predictor, our outcome variable, and blood levels and mother's IQ are our predictor variables. And I always like to get it to flag significant correlations for me. And I always want to see a plot for a correlation matrix. And go ahead and add these densities and statistics because those make things easy to read. Okay, so if we look at child's IQ, which is our predictor or our outcome variable, we see with mother's IQ, that's a very strong correlation there. And child's IQ, oh, I'm sorry, I read the wrong column. Really easy to make a mistake here, so let that be a just example to you of being careful. Child's IQ with blood levels, really high correlation there, negative 0.913. Try and remember, okay, it's a negative correlation. What's the strength and direction? The strength, 0.9, really strong. Negative, that means as one variable goes up, the other variable goes down. And it doesn't matter which one you say first or second because it's going to be correct as long as you have them going in opposite directions. As child IQ increases, blood lead level decreases, or as blood lead level increases, child IQ decreases. That direction is always going to be correct. And then child IQ with mother's IQ, 0.709, also a strong correlation, not quite as strong as with blood lead levels, but this time it's a positive relationship. As mother's IQ increases, child's IQ increases. And we can see from these scatter plots, I don't see any really strange curvilinear relationships here, as one goes up and then it starts going back down again. And so those look pretty good. Those look pretty good to me. The one that we didn't look at closely is blood lead level and mother's IQ. And we can see that if we go to mother's lead level and mother's IQ and blood lead level, that it is correlated a negative 0.6. For most correlations, that's kind of a moderate correlation. It's starting to go towards the high end, and it is statistically significant. And then the question is, are these predictive variables so highly correlated that it's problematic for us? And our guideline is that if it's about 0.8 or above, you want to consider that the predictors might be too highly correlated, and you should consider leaving one out. But 0.6 or below the 0.8, and we should be okay with that. Okay, so we looked at these things about our data set before moving into our analysis. Okay, so answer the questions in section 3, test information for the model overall. So we're going to focus mostly on the model. So let's look at our test selection. We had looked at our table earlier, or you should have looked at this table before. I'm going to bring it up so we can just take a peek at it. When we're deciding what test should we use. Up to this point, we've mostly been building on this table, one dependent variable, one independent variable, but we made a second table that is one dependent variable and more than one independent variable. So, and on this, if we look at our dependent variable and we're down at the continuous, the interval, and ratio lines, we can see we have our new test added here for all levels of measurement, multiple regression. So we're going to have a continuous outcome, and we can have one or more independent variables that are any of our levels of measurement, nominal, ordinal, interval, or ratio. So something that I'll tell you how I was trained, but I'll tell you how I hear things done in practice, is the term multivariate statistics. So when I was trained, when you hear that term multivariate statistics, that is referring to the dependent variable, your outcome. And if you have a single variable as an outcome, that's a univariate statistics. It doesn't matter here in multiple regression, even though we have multiple predictor variables, we're still focused on a single outcome. And this is still univariate statistics. All of the statistics we talk about in this course this semester are univariate statistics, even though in some of these tests we have multiple predictor variables. I hear this used incorrectly all the time, and people often say multivariate statistics because there are multiple predictors there. I just want to teach you, for people that are trained a lot in statistics, when they say univariate statistics, they're talking about the outcome variable only. And so just be aware of that distinction. You are going to hear people say it differently. I just want to make you aware. So, okay, which statistical test? We know that we have our continuous outcome variable. And let's take a peek at StatCat. So if you're ever not sure what you can be doing, then StatCat might be able to help you out. So let's go take a peek at it. StatCat, relationships, prediction, and group comparisons. We're doing prediction here, prediction of our continuous variable. And we know that child's IQ is our dependent variable, and blood lead level and mother's IQ are our predictors. And notice that once we have multiple predictors, that Jamovi guides us toward a linear regression analysis. So that is helpful, and then it gives us a couple scatter plots just to give us an idea of what the um, data look like with child's IQ and their predictors that we specified, and we can see that negative relationship with blood level and positive relationship with mother's IQ, so that jives. And I'm sure if you went and asked ChatGPT if I have a continuous predictor variable and continuous outcome variable and two continuous predictor variables, the ChatGPT probably do a pretty decent job of steering you to the test, because the tests I've done with it so far were pretty good. Okay, independent and dependent variables. Our dependent variable is continuous. Independent variable 1 is any level of measurement. Independent variable 2 is also any level of measurement. So our test assumptions: the sample is randomly selected from the population. That we know that from study design. Observations are independent. We know that from the study design. Data are normally distributed. We can take a double check. I don't think we went back and after we fixed our one bad data entry, and if we look at our Shapiro-Wilk test, we don't violate our normality for those variables, so we're probably pretty okay. Whoops. Variables have a linear relationship. We looked at scatter plots, and it looked pretty good using the eyeball test, which is what I was taught as a student. Call it the eyeball test, and that's a pretty good test. And we'll see, we can actually put some numbers to it later with some more, but we should be okay. And our homoscedasticity, we looked at those scatter plots, and they looked pretty okay. There are some other tests that we can look at. So then our null hypothesis significant test steps. For a regression model, the null and alternative hypotheses are: there is no difference between the model with predictors and the null or intercept only model. And the alternative is there is a difference between the model and the predictors, with the model with predictors and the null or intercept only model. And then we're going to go look at our test statistic there. So this is probably a good place for us to go ahead and put this in Jamovi, and let's take a peek at it. So let's go to analysis, regression, and linear regression. And as soon as my computer catches up, now we can take our outcome variable, which is child IQ, and move that to the dependent variable box, and then we can drag blood lead level and mother's IQ down to the covariates box. You will see that there's a factor box here. If you had a categorical variable, you could actually drag it here to the factors box. We're not going to try an example like this, but back when I learned, I had to recode things manually and do some playing around with the data, but Jamovi makes it a little bit easier if you have a factor. And remember, a factor is just a variable that divides people into groups. Jamovi can help you out with some of the coding that's needed to make it usable in a regression. So just remember that factor is a categorical variable, but we're using all continuous right now. And let's go ahead and go to our model fit. And we have our R and R squared. So we have a model, we have R and then R squared. So we're explaining 85.6% of the variance in our outcome variable with our predictor variables. And we do want to get an adjusted R squared because we do have multiple predictors. And you'll see that this R squared went from 80.85 0.856 down to 0.814. So adjusting for multiple predictors, we went down. And I typically am pretty conservative on statistics, and I lean towards the side of, if you have multiple predictors, focus on the adjusted R-squared. And then we want our overall model test, our F-test. And then the question is our model significantly different than the null model, the model with just an intercept and no predictors? And we get an F value for 20.7 and a p-value of 0.001. That is statistically significant. So we'd reject the null and say there is a difference between the null model and the model that we just created. Okay, that is a good place to move to the next section. You'll notice that I moved this post hoc to another slide just because there's a good bit for us to hear to talk about here with this post hoc testing in the model overall. So you saw in the Navarro text that Navarro talked about regression diagnostics or model checking. So there is this kind of bit of a process you go through when doing regression, and really this is, not just a straight up linear process. You really kind of go back and forth a bit. So this is a good place to just look at some of our things about regression in this model a little more closely. So go ahead and look at the assumption checks section here in Jamovi, and we actually get a number of tests. And I don't think Navarro talked about all these, but we can click a box and get a number here. And so I'm just going to go ahead and tell you guys about these different assumption check boxes here. So autocorrelation test is looking to see if the data, the residuals are correlated with each other. And I looked this up, and this Durbin-Watson test, this is not something I was actually taught as a student, but we can click a box and get it. So, and really easy to Google something. And so what it said was these values go from 0 to 4. 2 means that you have no autocorrelation. Down to close to 0 means you have a problem in the negative direction, and up close to 4, a problem in the positive direction. And what you're looking for this test is it should not be significant. And we see we have a p-value of 0.418. It's not statistically significant. We don't have a problem with autocorrelation. So we can get the test. We can look it up easily, easy enough to use it. We don't have a problem. So we don't have a problem with our residuals being correlated with each other. Collinearity statistics. This is where I told you guys about this variance inflation factor. And you'll see this other one called tolerance. These are actually just inverses of each other. So if you put 1 over 1.174, you'd get this 0.573. So this is a test for looking for collinearity. And we had already looked at our correlations and saw that our predictors, it's collinearity between the predictors. And we'd seen that between blood lead level and mother's IQ, that correlation was like about 0.6. We decided that wasn't a big deal because we weren't reaching our threshold of 0.8 or above. And not surprisingly, this variance inflation factor is 1.74. The guidelines that I was able to find, and I think Navarro gives these too, is that 5 and above, you might want to start looking. There might be a potential issue. 10 and above, you got a problem, and you should probably make some sort of an adjustment somehow, meaning leave one of those highly correlated variables out of the analysis. Pick one and use that instead of using them both. We're down close to 1. We have no problems with multicollinearity here. And I was trained to always look at those scatter plots before running a regression, and that's a perfectly acceptable way to do it. But these things reinforce each other, so it's nice to see how that works. Our normality test, that is the one that we're used to, our Shapiro-Wilk test. And again, we looked at it before and it wasn't significant, and it's not significant, so we're good with that. So a QQ plot of the residuals. So this is looking at the residuals, which are those values from the predicted value to the actual value. And this is just looking at these along the normal line here, and you want your values pretty close to that. And they're pretty close. So it's just another way to check for normality, and we don't have a problem with our normality assumption. And now these residual plots. And Jamovi goes through and looks at the difference between our predicted values and our actual values, and then it plots them. So those are the residuals, and it plots them against a couple things. So fitted, that is our predicted values for each variable, for each observation, based on the prediction equation that we looked at. We haven't looked at it too closely yet, but what you want, you'll see it has 0 on the y-axis, and then it goes up and down, and you want your data to be, your residuals to be fairly well evenly spread above and below that 0 point. And these are pretty, randomly, there's no real pattern here, and so that's good. And what these are helping us to see is if we had a problem with these residual plots, we may have a problem with our linearity, our homoscedasticity, and our independence assumptions, and we're not seeing that. So then we have our residuals against child's IQ. They're pretty evenly distributed. I mean, this is a small data set, so it's not going to be perfect. Residuals with lead level, again, are we spread around that? And you'll see we're going above and below fairly closely the similar amounts. There is one that's kind of down here below some others, -10, as we're going to see this one will come up again later. And then residuals with mother's IQ, and we are pretty evenly distributed there. So that's all pretty handy. And then Cook's distance. So I'm going to leave that one for just a second till when we start talking about the individual observations and the variables themselves. So I'm going to leave base factor for a second, and our effect size, our percentage of shared variance, we'd already looked at, which was our R squared and adjusted R squared. And adjusted R squared, we're explaining 81.4% of the variance in our outcome variable with our predictors. Okay, now that we kind of looked at our model overall, now we're going to go through these tests and look at our variables in the model, or our individual predictors. And again, we had looked at our assumptions. The null hypothesis for any of these tests is that the b is equal to 0, and the alternative is the b is not equal to 0. Again, we're just using 0.05, and we're going to look at our test statistics and then decide, do we reject or fail to reject. So I do want to get one extra thing here, and that's a standardized estimate for our variables, our predictor variables. And we're going to go into this model coefficients menu right here, and we're going to get a standardized estimate. So if we look now, before we looked at this model fit measures, which was our model overall, and now we're looking at our model coefficients, our predictors, and let's look at each one. So blood lead level, this is the same one that we had last week, and last week it was significant, and we see that our p-value is 0.004. That is statistically significant, and so if we're going to report this one, we report the t and the standard error and the p-value. And like I said, I think I told you guys last week, if you were reporting results of this, often this table is what you would put in your report, because people want to see these values for your individual predictors. So mother's IQ, we have a t of 1.04. That's pretty low for a T, and a p-value of 0.332, and that is not statistically significant. So in this regression equation, blood level is statistically significant, and mother's IQ is not statistically significant. So that's not doing a lot here. And we kind of glossed over a little bit these standardized estimates. You can't really judge or compare predictor variables against each other using the non-standardized estimates because the units are different. So blood level is in whatever the level is for how they measure that, and then mother's IQ is in IQ units. Those things are just not the same. This is truly an apples and oranges comparison. They're not the same. You can't use these raw unstandardized coefficients to compare those with each other. But as we learned with z-scores, we can convert things that use different units into z-scores and compare those with each other, and that's what these standardized estimates do. So we can see blood level has a standardized estimate of negative 0.784, and mother's IQ has a standardized estimate of 0.198. So in standardized units, negative 0.7 is quite a bit bigger than 0.198. And so blood level is the main predictor here, the stronger predictor here. Even though it's negative, it's just affecting things. So when it comes to the prediction equation, you want to use the unstandardized estimates because these are what you use to do actual prediction. And you would use these unstandardized estimates to make a prediction equation. And in this case, our prediction equation would be predicted child's IQ is equal to the intercept, 99.624, subtract, because this one's negative, 0.42 times the value of the blood level for that observation, plus 0.18 times the value for the mother's IQ. That would be our prediction equation for this regression model. But to compare predictors with each other, you'd use the standardized coefficients, and definitely you want to get the one with the biggest absolute value there. That's going to be your stronger predictor, and then you look for the next one, and sometimes you'll have a number of variables, and you could compare them using the standardized estimates. So unstandardized estimates are used for prediction, standardized estimates are used for comparison. Okay, and now we want to look at influential cases. We've kind of looked at individual variables, and we're going to look at some individual cases. And so we will go back to our assumption checks, and you'll see under the data summary, we have Cook's distance. So if I add Cook's distance in there, we're going to go look at Cook's distance, and you'll see it gives us a mean and a median, a mean of 0.5. And then we get a range, a minimum of 0.003 to a max of 3.83. So for Cook's distance, values above 1 are potentially problematic observations. So we would want to go look at if we have a value. And this is just a summary table. We don't really, all we have is a range here. We don't know which value has 3.83, but Jamovi has a way for us to look at that. And so we're going to go ahead and go down to this save box. So if you go down to the bottom and click on the save box, we can actually get some things, and these actually get added to our data set. So we're going to go ahead and just get all three: predicted values, residuals, and Cook's distance. Now if we go back up to our data window and click on that, you'll notice that now we have 3 additional variables in our data set. And our predicted values, our residuals, and Cook's distance. So predicted values, these are just the values. If you use the regression equation on each of these observations and calculated what would be the predicted value for that individual, that's what those are. And if you look in your HEVI text on page 196, the bottom table, you'll notice that HEVI demonstrated having those predicted values there also. And if you compare our predicted values with HEVI's predicted values for each case, you'll see that they match. Residuals is taking the predicted value and finding the difference between the predicted and the actual value. And so if you took 125 was the actual value for this, and subtract 118.36, you would get a residual of 6.674. So that's all these residuals are, is the difference between predicted and actual. And then Cook's distance. So it calculates a Cook's distance, and we're looking for influential cases, and we're looking for cases where it's 1. And you'll see we're all pretty low. There's 1 here on row 7. It's 1.058, so just barely above 1. But here on row 10, 0.3827. So, and I think this happens to be the one that had an outlier for blood lead levels. So potentially that could be a case. And really what you want to do is go back and look, 1, is there any kind of data entry error? And 2, why is that individual so different from others in the data set? And if you can identify a reason why it might be appropriate to leave that one out, then you might consider that. But you want to have a really good justification. You don't just leave somebody out because they're an outlier. That's not a good enough reason. You really have to have a reason why, is this one different? Was this individual in a way different setting than other individuals? In which case, you're focused more on what's generally applicable instead of an extreme case. That might be a good justification, but that's something you could think about. We're not going to change anything here, but just be aware that was something that you would look at as part of your evaluating this regression model. The effect size for individual cases is that standardized estimate. So, that's closest to you're going to get to an effect size for individual estimates. So our standardized estimate, those would be kind of the effect size. And then we'll look at, we don't have Bayes factor for individual variables here. Okay, let's see, what else do we have here? So do look at your Jamovi results with page 196. Unfortunately, on page 196 in the top table, last week, Hebe had made a mistake and put the standardized coefficients heading over a standard error column. And this week, Hebe made a different mistake and put the standardized coefficients label over the T column. The T column are not the standardized coefficients. The T column is the beta column. And last week, Hebe had also made a mistake and put the values for the betas starting on the constant row. And if you look at Hebe's table, you look at the standardized estimate, you'll see that this negative 0.784 is actually up on the intercept row, and then 0.198 is down on the BLL level, and the mother's IQ is blank, and that's an actual error. So the intercept, when you standardize, you make it a mean of 0, standard deviation of 1. That means our intercept is our mean for our sample, and that's going to be 0. So the intercept, the standardized estimate on a regression equation, the intercept is always going to be 0. And then negative 0.784 is the BLL, and 0.198 is the mother's IQ. So that top table on 196 in Hebe has some more mistakes in it. So just be aware. You think when you see things in print that, there's 5 people checking this, it's going to be okay. This probably had to go through a number of people to get this mistake, and mistakes do make their way through a system and a process. So be prepared to double check things yourself. Okay, so since we're here in Jamovi, I thought I'd go ahead and show you guys a model selection test or steps, because it's not too hard to do. So if we click back into our model, our regression section, and we're back into our menu, here. Just click in one of these tables in Jamovi, and you'll get the menu back for the regression model. And we're going to go to this model builder here. And so when we did this regression, we dragged our dependent variable, our independent variables over to the window, and Jamovi created this model for us. And it had blood lead levels and mother's IQ. So we're going to add a new block. So click on Add a New Block, and now you see we have a block 1 and a block 2. We're just going to drag mother's IQ down to block 2. And what this does, it tells Jamovi, I want to treat these as potentially separate models, and this does this by first it makes the block 1 model, and then it will go and take whatever is in block 1 and then add block 2 to it. So the block 2 model is equivalent to what we had before, but now you'll see we have a couple extra lines here. So on our model fit measures, now we have 2 models, model 1, and if you went back and compared our simple regression last week that just had blood lead levels, you would see that these values exactly match our model that just had one predictor. And then you can see that now we have another model, and we also get a significance test, and this matches what we had before when we had both those predictors in the model. And you'll see they're both statistically significant, different than the mole model, different than the null model, but we have an extra row here, the model comparisons. And this is comparing the first model with just blood lead levels to the second model, which has blood lead levels and mother's IQ. And what you're going to see is these are not statistically significant. They're not statistically significantly different from each other. So adding mother's IQ did not really improve things. It's not enough to make it statistically significant. So this is a pretty neat way for if you're deciding what model is the best model. The first one did a lot, and the second one, it didn't add that much by adding that extra variable in. So you'll notice down here under the model specific results, we have our coefficients table, but we have a new extra little drop box, and we can go select between model 1 and model 2. Now you might think to yourself, oh, mother's IQ is not statistically significant, so I can report these values without including it. But if you switch between these two, you'll notice that these values actually change. Anytime that you add a variable in or take it out, even if it's not statistically significant, it changes all of your estimate values there. So if we, here in the model 2, blood lead level, the estimate is 0.42. If we go to model 1, it's 0.489. So anytime you change the variables in the model, even if they're not statistically significant, you have to go recalculate the model with just the variables that you want to keep because the values will change. Same thing with our standardized estimate for blood lead level on model 2 is 0.784, negative 0.784, and under model 1 it was negative 0.913. So adding or taking away variables definitely changes all your numbers, and you have to go recalculate if you want to do a final model that's different than the one you have. Luckily, we can just switch between them here on our output in Jamovi. That's pretty handy. So SPSS wasn't like that when I was a student. Okay. The other thing that we're going to add in is under model fit, we have some other things, AIC, BIC, RMSE. We're just going to focus on AIC. In an AIC, the lower the AIC, the better the model is. So if we add AIC in and we go look at this, you'll notice that model 1, which we're back in our model fit measures, has an AIC of 69. That's just the model that has blood lead levels. And you'll notice that model 2 that adds blood lead levels and mother's IQ has an AIC of 69.6. So model 1 actually has a better AIC, a lower AIC, than model 2, meaning that adding that extra variable in probably didn't help us out. It probably hurt us a little bit. It made the model more complex when it really didn't need to be. I just tell you, BIC, it's interpreted the same as AIC. That stands for Bayesian Information Criterion. Lower values are better for that. RMSE stands for root mean square error, and that's just a pretty simplistic way to look at errors. The higher the errors, the more error there is, and we're not going to focus on them, so don't worry about it. But as you add more variables in the model, that root mean square error is going to go down. I know. Thank you. It's going to go down. So just be aware, but we won't focus on those. So yeah, if I were picking one model here, I would go with model 1, the one that just had blood levels. And whoops. So which model seemed the best? I would go with model 1. Which predictor seemed the most important? Blood lead levels. And then just for the heck of it, let's try and see how well this reports some results for us. So if I go copy our my prompt here, please help me report the results of a multiple regression. And let's open up ChatGPT. All right, we're going to hit Shift Enter to go down to the next line, and we'll bring up our linear regression. So let's go ahead and paste in this model fit measures. Let's right click on the table and hit copy, and then Control V to paste, Shift Enter to go down to the next line. Let's go ahead and put our model comparisons in. And I've not tried this yet, so this is a total experiment, but this is a great time for us to experiment together. So we copy that table, Control V to paste, Shift Enter, and model specifics. Let's go to model 2 and right click on the table and copy, and let's go into ChatGPT, Control V to paste, and let's hit Enter. And let's see how ChatGPT does with helping us interpret and report results for this multiple regression. I think if there's anywhere it would make a mistake, it might be here because this is getting more complex. Okay, a hierarchical multiple regression, which is correct when you do things that have the same models and building on each other, is called a hierarchical regression, so that's good. Was conducted to examine the effects of blood lead level and maternal on child IQ. In model 1, which included blood lead level as the sole predictor, the model was significant. Those numbers are correct and explained a large portion of the variance in the model with adjusted R-square and AIC of 69. In model 2, maternal IQ was added to the model. The overall model remained significant, F27. Those are correct, with R-squared 0.856 and adjusted R-squared 0.814. However, the additional maternal IQ did not significantly improve the model. Change in R-square with an F-test of P.332, not significant. That is correct. Examining individual predictors in model 2, BLL was a significant predictor of child IQ. B, the unstandardized estimate with the t-value and a large standardized coefficient, beta. See, it's using the B and beta the way that I was taught, so ignore Hevy. indicating that the higher BLL was associated with a lower title IQ. Material IQ was not a significant predictor, B of 0.1, 0.18, standard error, T value, P with a beta of 0.198. Dang, you guys, that's pretty good. It really, you could ask for it to change something, but all that information is correct, and it did a pretty nice job of taking those results out of those tables and putting it into something. I gotta say, I'm quite impressed. I would have loved having a tool like this when I was a student. Okay, so copy that that write-up and click on the bottom of your Jamovi output if you're going to go through the work to get it. Save it with your output so you have it for later. You can come back to this all together and see it, and be reminded of what you were doing. Okay, man, I'm still a little surprised by how well that worked. Save your Jamovi data file. So hamburger menu, file, save as, and then put your name on it and save your data file. Let's turn that off. And then our next one is a PDF of your output. So file, your hamburger menu, which I always look at as the file menu, export, and we want to save a PDF. Browse to go to your correct folder. Make sure it's in the correct place. And you want to turn your PDF of your output in. Answer the computer assignment questions and submit your PDF output in Canvas. So this was a longer lab, but it's looking at these options in for regression in Jamovi, and understanding how this works is going to benefit you. Understanding research, and do they tell you they've looked at their assumptions or not? That's a real sign of quality. If they've checked them, that's great. So I hope you have a good day and a good rest of your week, and we'll talk to you guys later.